Hey guys, this is going to be some review on how to solve your momentum problems for the egg catcher. So the first thing that we need to do was to measure the mass of an egg, which I just did, and I got one to be 60 grams. To go from grams to kilograms, you're going to divide by 1,000. So you would say that 1 kilogram is 1,000 grams. So I have 0.06 kilograms is my mass. All right, and then I'm going to figure out how fast it's going when it gets to my device. And I'm going to say that my device was 30 centimeters. It's possible that yours was a little bit less than that, but it shouldn't have been more because the limit was 12 inches. So for my first chart, which is for the 1.5 meter drop, my initial velocity is going to be 0. My acceleration is going to be -10. And the distance that I'm going to drop is going to be -1.2. So even though I'm dropping it from 1.5 meters, I'm going to cut off that 30 centimeters because it's going to be a different math problem once it actually gets to the device. For my other chart, my 2-meter chart, it's going to be 0 meters per second, -10 meters per second squared, and now this is going to be a 1.7 meter drop. All right, so I'm interested in the final velocity. I don't really care for how long it's going to fall for. So what is my final velocity as I reach the device? And so I know in kinematics that v squared equals v naught squared plus 2a x minus x naught. So v is going to be equal to the square root of 2 times -10 times -1.2 square rooted. And for my other chart, it's going to be 2 times -10 times -1.7. So for my smaller one, the less fall, it's going to be about 4.9 meters per second. And for the bigger one, it's going to be 5.8. All right, and again, yours will vary a little bit because it's not necessarily what you have for those. All right, so I'm going to make some room for myself. Okay, so calculate the momenta the egg would possess as it reaches the device. So momentum formula is m times v. So for my 1.5 meter fall, it's going to be 0.06 kilograms times 4.9 meters per second. For my 2 meter fall, it's going to be 0.06 kilograms times 5.8 meters per second. The weird thing about momentum is it doesn't have a new unit. So it looks like I have 0.294 kilograms meters per second and 0.38. Sorry, 0.348. So why don't I just make that 0.35? And I'm going to give both of those a negative value because it's going down. All right, so I'm going to scroll and see what they ask for next. All right, so if this is the momentum for each one of them, the impulse is going to be the positive value of this. So if I have negative 0.294 kilograms meters per second that I need to cancel out, I need positive 0.294 Newton seconds of impulse. So it's going to be positive 0.294 and positive 0.35. And very often when we're talking about impulse, we talk about the units in terms of Newton seconds. It's the same as kilograms meters per second. All right, so I said the height of my device was 0.3 meters. I'm going to take my velocity from number 3. So, I got to answer these. Which is a larger force, the force on the egg or the force on the device? These would be the same, right? There, it is Newton's third law. So it would be an action-reaction pair. The egg will hit your device just as much as your device would hit the egg. All right, so I'm going to have another one, and we're going to say that we have the height of our device is 0.3. Why don't I work up here? So I'm going to have two charts. I'm going to have, I'm going to say the height of my device is 0.3 meters. I'm going to say my initial velocity is 0.49 meters per second. I'm sorry, 4.9 meters per second. And negative 5.8 are our two speeds. And again, since it was down directed, I should have them as negative values because the acceleration is going to be positive. All right, the final velocity for each of them is going to be 0. Whether they cracked or not, right, they're going to stop. And I can get what my acceleration is and then also what my time is. So for this, I can say that v squared equals v naught squared plus 2a x minus x naught. Do I need the impulse again? Yes. So I'm going to write those down so I have my impulses. Because I don't trust myself to remember that. So I have 0.294 and 0.35. So we'll need that to calculate our average force. And I'm assuming that this is a constant acceleration. It's probably a pretty big assumption. All right, so I can say that acceleration would be equal to v squared minus v naught squared over 2 x minus x naught. So this is going to be 0 squared minus our initial velocity. So that's going to be negative 4.9 meters per second squared over 2 times. And since it's going to travel down, this should also be a negative. And then my other acceleration is going to be 0 squared minus negative 5.8 meters per second squared over 2 times the same height. And it's possible if it cracked the first time, you didn't get a chance to do a second one. All right, so I have $40 And I have $56. All right, so I'm going to erase this so I can do the times. So V equals V naught plus AT. So V minus V naught over A would be your T. So this is going to be 0 minus a negative 4.9 over a positive 40. And 0 minus a negative 5.8 over positive 56. So for the larger distance, I have a 0.1 second. And for the smaller distance, I have like a 0.12 time. All right, so I'm going to erase this. A little more review, taking us back to circular motion where we talked about G's. 1 G is 10. And so for this one, I would have 4 G's for the smaller fall and 5.6 G's for the bigger fall. Then I want to find my average net forces. So this is F delta T equals M delta V. So my force is going to be my change in momentum over my time. So for one of these, it's going to be 0.294 Newton seconds over 0.12 seconds. So I have 2.45 newtons. For the other one, it would be 0.35 Newton seconds over 0.1 seconds, which is 3.5 newtons. So that's for the bigger one.